much for inviting workshop. So my title is very vague. I will just stay as much high level as possible to give a little different ideas on how to achieve the physical intelligence. This is, everybody's in this table, probably, we don't need to even worry about this. Like, we are all moving from information service to the physical service, which is really exciting, especially for roboticists. But yet, I think if you look at all the real environment, real commercial environment, the robot hardwares are not ready, because this is a space we've been stuck in last about 50 years. And if you look at even most modern, the robotics companies, they're still using pretty much very rigid position following robots. And that's what you see in the factories. That's why we observed in 2015 with all these amazing looking robots. But inside, the robots are pretty much position following very rigid robots. So first 10 years of my career at MIT, I've been pretty much focusing on how can we get out of this, stuck space where everything is position control. If you miss position, you're done. There's no way adaptability. It's not like our human finger, you need to worry about collisions. We can be actually very adaptable. So I'll quickly show you some of those results, mostly on the quadruped robot. But this problem haven't solved in the manipulation yet. So you're watching quadruped robot running, but the essence is not about quadruped running. Yes, there's algorithm, they're coding, jumping over obstacles, yeah, but that's not the point. The point is being able to embrace contact and collision, and while still reason about the contact and then be able to react. And then the hardware wasn't even ready until we actually show how to do it. This is actually work from a Kwan. I think he's a professor here. You see now. And we did some teleoperation working 10 years ago using proprioceptive actuation. Is actually much more dynamic, less precise. So something you have to aware of. There's a lot of price pay for it. Like if you go to I want to be compliant force controlled actuation. Now a lot of benefit that we've been stuck utilizing this position accurate machines is gone. Not completely gone, but a lot of things are compromised. And then your control engineering has to be much rigorous, much more difficult. And also the quality of the hardware also need to be much higher. If you just stuck like a pretty decent, like a harmonic drive and then very rigid, decent position control, that's all you need. But once your robots are not rigid, now you have to watch out for every single frictions and impedances, and you need to know the model much more carefully. The reason why all these manufacturer robots are following this rigid regime because you don't need to model that well. They do model, but they're all targeting to really get into this sub-millimeter, sub-100 micron accuracy. And that's what we've been stuck on. And the idea I presented 2010, 2009 is actually proprioceptive actuation. You can actually force control the best bandwidth in the world with the simplest system. And you can see some difference. This is also about 10 years old video compared to all these teleoperation video you saw recently, especially in all these companies. And my hand actually can feel all the forces with the zero force feedback. There's no force sensor, but I feel the forces. There's a force feedback, but so my brain is actually getting feedback to handle this. But the bandwidth and then how can I say, the reliance upon impact and so on is just remarkable. And this quite hasn't happened in the manipulation yet. The main reason is, even though this is 10 years old, we've been doing this more than 15 years, is the algorithm has become much more complex. And I'll talk about how we're going to handle that. So fast forward, after we published our cheetah work, which is all red, now the penguin explosion mostly happening in China. And you can see the unit tree is happening, and Boston Dynamics is using our stuff. This is my student actually designed it, and so on. So if you go to the MIT, our lab, actually our robot humanoid looks like this, and there's a lot of computers and infrastructure. But literally, whenever we build a new robot, this is only one that we change, which is pretty much aluminum pieces. And we can literally design our new hardware with this force control, the compliant, and so on. Let's step into a little bit of the locomotion. If you really think about why locomotions and the teleoperation space is so different, because locomotion is a lot less visual dependence. yes, I need to balance myself, but a lot of feedback is happening in the proprioception. Whereas the manipulation, we are actually a lot more visually dependent. That's why BLA, we're relying on visual motor control algorithm a lot more. Whereas locomotion, we actually rely a lot more on physics of parameters, with like MPC, we look at the physics, and also reinforcement learning, which actually implicitly learn the physics, right? I just want to point out there's such a drastic difference between these two approaches, because one, literally just like I will experience as much as possible and then I'll behave based on my experience, which is pretty much data-driven approach. Whereas MPC, I can reason any situation as long as I'm within the assumption, but I have no memory. Every single time step, I'm going to gradient descend as if I have no memories. I think there's both have definitely a flaw. If you fall into a situation you've never been, you're going to do something random. You see all these overfitting problem in the data approach. No matter how much data you collected, you see the Tesla 7 million cars and all that is still having issues. This one can reason about it, but it's very brittle, only within the assumption. It takes a lot of computing and doesn't know how to use the memory whatsoever. So we need to really think about how to combine it. I'll show you one example. We actually have a much better algorithm developing, but this is something we published. I think we should skip because I talk about the difference between these two. One is we are actually getting a physically informed cost function to guide the reinforcement learning to behave to this. So this is just walking, but actually you'll see the turning and 180-degree turning as well. So if you ask one task, RL actually can do all this. But the problem is if you try to do multiple things like turn left, turn right, slow, fast, many things, RL kind of suffer because somebody needs to cost function tuning for every single case. And then the one cost function set doesn't really work for the other one. So nowadays, if you look at the best reinforcement learning work, the most of the focus is actually planning side, like sample based. If you look at Pangbo Jamin's work at the KAIST, the vast majority of the work is actually creating architecture to really help the reinforcement learning to do the right thing. So this is one part of the work, and you can see the benefit of having model-based or some other heuristic help the reinforcement learning to learn better. And I'll show you some other just random humanoid work we did. This is basically the same thing, model-guided reinforcement learning. And then the rest of the work is actually all model-based only. So you can see the model-based is not as smooth and not as nice because it doesn't learn all these details and implicitly when RL does. But the model-based can do so many things at once. So one framework, I can do many things. I'm not saying this is the best performance. We can probably can do more if you add RL on top of it, like similar to what Sergey was showing. RL can be very, very powerful to grounding all the previous work. So high-level planning, and then the model-based approach can plan the whole body dynamics, and then RL can basically finish the game. Let's switch to gear, and I want to talk about manipulation. I have a short history in work with manipulation, but I can tell you what I learned last 7 years or so. This is basically me picking an apple, and then I asked my student to take a video, and then I'll play one more time. This is how quickly I can pick it up, and this is the worst case scenario. This is not happening every single time, but look at I crash into the apple, and then try to grab something. I didn't know that my hand is such a simple, like detect something, grab it. That's the basic algorithm running, and then it failed it. While failing, you're in contact with the 5-6 different apples, and then I don't know why my hand chose the worst possible case. If you look at it, like if you write an algorithm here, I make a contact, you should probably choose the highest, the closest, whatever. Like no matter how simple your heuristic, you go with the left one and the right one. Somehow my hand choose the worst possible choice. And then you have to dig your finger into it. And then you couldn't quite get a good grasp, so you have to delve into another one. What's remarkable is, if you can see, my hand does plan A, situation doesn't work, plan B, plan C, plan D. So all these things happen in 0.7 seconds, including reasoning and action. Do I remember any of these actions? Absolutely not. I don't remember any of these. So I'm really trying to advocate system 1 versus system 2. We really need to focus on system 1 because there's a lot of work, especially previous presentation shows amazing progress on system 2 side, like reasoning, visual-based reasoning. Of course, there's a lot of fine manipulation happening. But those are still relying on our visual surveying. The reason why we see this amazing demonstration, because humans are so good at teleoperating those robots, and then we're looking carefully, and then visually reasoning, even though you don't feel it. Speaking of visual reasoning, I mean, you can see in the surgeon, using the Da Vinci surgeon. I'm not sure if you tried it. It was amazing. I don't feel anything here, but I can actually reason about what I'm doing with the flash and cutting and everything. So it is amazing how much you can do with the visual surveying, piggyback on human intelligence, right? Like we're literally copying what humans do. But I think there's still more to do, especially really when we reach like a 95% success rate, really getting close to 96, 97. The amount of data you need to collect, the amount of like meticulous engineering is going to skyrocket. So really, you need to think about what you just saw, what my hand was doing. You need to think about how you do it. And I'm not saying what we are doing is actually the best way. Just an example and baby steps. So just don't take seriously. But this is what I did at IT and Andrew Salopoulos, and we basically create a reflex layer, which is basically very little reasoning, but it's very good at one masters. Imagine you're machining, I don't know, like 20-meter robot, and then you have a army of engineer, and then at the end, somebody was very good at CNC milling machine, like give him a drawing, and he was machining. So I don't need to tell him too much about it. So imagine having this little army of hollows which can react really, really quickly. As you can see, this 0.7-second grabbing apple, my finger was doing a lot of those reflexes, where my brain is completely unconscious about it. Anti-slip reflex is pretty cool. I think this is actually happening every single time when you pick up something. You're not aware of it. Whenever you pick up something, you don't know how heavy it is, and so you put the handle on the vehicle roughly aggressive, and then when you pull, you feel like, oh, this is heavier than you expected. You actually increase your contact force to match it. So that's basically what we created, because we have a sensor that measures contact location and XYZ forces. So this thing might happen. I'm not sure if you can see it. If you pick it up, and then when you pull down and increase force, the robots are actually squeezing more proportionally. It's trying to stay in the friction cone. Another way to demonstrate is for water, initially grasp force is constant, and then when weight goes up, your grasp force goes up proportionally, so you can actually adapt on these situations. So this kind of behavior, very hard to get from VLA. Yes, those companies use a flex gripper, so you can get some of it. I wouldn't be relying on that subtlety depending on stiffness of the gripper. When you change the stiffness, all these things is going to be not reliable. This is regressive reflex. This is also a little subtle. It's hard to see. Again, it's a very simple example. So using anti-photo, like, am I grabbing in the middle or not? It's not generalizable, but you can make it generalizable with a little more complex algorithm. So you can see that like George, which is not human command. Human command to get closer, and then robot feels it and then move on like about 100 milliseconds. Very quick. This is slow motion, and then the sensor knows hopefully where we're heading, and it's going to slip and then regress. So if you can see, these are all teleoperation, but with the reflex, without reflex, the performance difference is drastic. Because human has to be, humans are very good, but if you've never done this kind of teleoperation, your position accuracy will be suffering. And the reflex basically take care of this. Not only the hand, actually entire arm actually react on it to improve the success rate. And you can see a lot of these jolting action. It's very hard to see unless you carefully see it. Like that shaking is actually not human command. Those are all autonomous. So human only need to command like roughly location, which hopefully we can achieve like 100% accuracy from BLA, and then we can finish the rest. So this is a little bit more complex. I'm not going to talk about everything. There's a very simple YOLO-based, location recognition, and then task is just grasping. But there's like regrasping, collision avoidance reflex. There's a dragging sucking into the palm, and then wrapping around. There's a few reflexes that are working in tandem. And you can see, again, it's a really simple task. So you can do this in many different things, but probably you won't be able to achieve this kind of speed. Because at the end of the day, we really all want a robot to achieve a similar speed and dynamics. And when it comes to dynamical reaction, all these visual-based, like position accurate following is gonna fail. We're not gonna follow that trajectory we do optimize for. So you need to be able to embrace this like inaccuracies and uncertainties, some unexpected collision. You should be able to recover using very fast policies. You don't need to talk to your CEO. This is the kind of analogy I talked about, like building a company. Like if you have a large model that does everything, you have to talk to the large model every single test situation, every single second. It's not going to be efficient. It's going to consume a lot of time. You're not going to be able to move fast. It's like you have a fire in your office and you're writing email to CEO. What is the optimal way to put out this fire and then waiting for the answer, right? So you want to be able to have some autonomy, and then I will show you some of the behaviors we can achieve with a very different type of actuator and very different type of sensors that can run 500 hertz, 1,000 hertz. We can actually behave. This is basically collision avoidance reflex that basically eliminates the need of the trajectory planning in traditional sense, trajectory planning of the finger. If you have a simple 1 degree freedom, maybe it's okay, but if you have a multi-finger and more complex system, you need to be able to react quickly to the occlusion and so on. You know, we just talked about following trajectory with the conventional robot arm is very rigid. You know, we get so far, we can probably go even more with just following copying what human intelligence trajectories. But I just want to tell you the comparison between the self-driving to the manipulation. Tesla has more than, I don't know how many millions right now, like probably more than 7 million right now. And then the car is a 2 degree freedom. And then the object, the car, if you think about a car as a robot, the object the car is dealing with is flat ground. Unless you have a SUV that climbing mountains, I don't think self-driving is dealing with that at all, right? So it's pretty much one object, one task. All the car tasks moving A from B. There's some uncertainty. There's either agent, this is probably the biggest uncertainty, and the perception uncertainty. Almost no uncertainty in action. I'm not sure if you thought about this. In autonomous car, if the plan or autonomous driving policy to create a trajectory, what is the chance of following the trajectory or not? 99.9999, unless we have a snow on the floor. So there is a zero uncertainty in action. Only uncertainty is perception and algorithm. When it comes to manipulation, I don't know how many robots each company has. Like Tesla, I saw 100 of them. Maybe some company have more than 100. Chinese robot company probably have like 300 maybe. Number comparison is just not matchable where the degree of freedom exploded. This is exponential. It's not linear. Like robot humanoid can be 40, 50. One manipulation arm easily have a 10 degree freedom. If you have a more finger, if you're a Tesla arm, Tesla hand has 22 degree freedom. One arm is 7 degree freedom. That's already 30 plus. Car has 2. Object, how about object? Are dealing with only flat object? We have object in the world, the variety is just crazy high. And car never make, do you guys still car jump and back, jump and land? No, right? We're making contact, breaking contact every single time. And test, I mean, it's a finite test, but it's, I don't know, it's 100 more than 100, but like roughly less than 100. A lot more than moving object. There's a perception uncertainty is actually comparable. Only good thing about manipulation, your objects are not moving around, maybe unless you're chasing mouse or something, right? And there's every contact, there's uncertainty. How you mitigate that uncertainty? Move slow and following the accurate precision trajectory. And then we can achieve some success. But if you try to start moving fast, all these things are going to go out the door. And how about standard language? Self-driving is still trajectory, still visual, still the kinematic space. Where manipulation, I don't believe that's the end of the story because you know to achieve really proficiency like approach to human level. I just want to say one more thing about imitation. I've seen amazing work from a PI, and then you will learn a lot of recoveries. But I will ask this question and then see if you can still apply to manipulation. Do you think you can train a robot to walk like human, collecting million people walking for 1,000,000 hours? Just think about it. This kind of street. Imagine you have a magic power, collect all the kinematics and even ground force, fine. Just collect whatever data you want. And then do you think you can train humanoid walking like a human? How many people you can do it? I'm talking about flat train. Wow, really? How many people you can train humanoid walking like human? No opinion? Really, like how many people you think seriously ask yourself how many people you can train a robot walk in the flight train like a human? I believe that we can do it. I mean, imagine like how much that's amazing amount of data. You should definitely be able to train robot walk in the flight train. My question is not that. My question is what happens if you shove it? How many data points from million people walking in million hours will have that recovery from the shoving? 2 or 3, right? Maybe if you're lucky, 10. And then how about direction? Shoving front, shoving back, shoving left, right? The point is, the imitation is the languages. Language is all about imitation. How you speak well is about you copy out somebody else's listening, right? In physical world, you can't just collect data, collect data to predict, expect, or to recover for every single situation because you cannot collect every single possible failure cases and recovery. That's the case. We'll see. I think the pie shows that there's a very, very large model, random action. Hopefully we can recover, but it's still just a hope. You probably can find a few anecdotes. In order to really guarantee, you have to make sure you have that data. We're not talking about, 90% success rate and then launch a product. 99% success rate robot is unusable in any cases. So I wanted to really think about what would be really true learning compared to this imitation and then just pattern matching. This is what Oscar Wilde says. He doesn't know anything about robotics and AI. Says something very remarkable. I still have some time, I guess, but similar to Tesla, to the autonomous driving, to the manipulation, there's just a large difference between virtual intelligence and physical intelligence. And all the benefit we expect from LLM, we're using as a human in the loop. Do you know any of the LLM like running autonomously? If an LLM really truly run autonomously, you can run a company, right? Right? You don't need to hire a CEO, you just hire LLM. There's not a single LLM fully autonomous, but we're fine with it. All these lawyer paralegals are going to fire it. I'm sorry, but there's a lot of white collar jobs is going to be eliminated. It's still very, very powerful. It's an amazing human intelligence. Yet, still human in the loop. Oh my God, same thing happened in robotics. Do you think robot can work in the factory with a human in the loop? I mean, that's what Waymo is doing, but their success rate to how many, I don't know how many car engineers working on it, right? And is it profitable? We have to really think about it, right? Human in the loop robot, this robot is 99.5, still okay, because human is gonna be there. What is the cost of that, if you really think about it? And then what is competitor? If you go to the factory and then warehouse, I've been in every single Amazon warehouse, and I've seen many factories. Their competition is severe because conventional technology is working so well. If you go Savannah on their factory, the car door is just assembled by itself. There's zero human input. And it's faster than human. So just think about what you're up against and then why it's so different from virtual to the physical world. And as I said before, virtual intelligence is actually their planning is everything. There's no quick reaction is required. When you write a sentence, I have a lunch, like do I react on the V sound and then react correctly? I think it's just like there's no like recovery action. There's no disturbance. In real world, and especially fast manipulation, everything you have to think about reaction. And then, but all the virtual intelligence we've been working on is pretty much is planning. And the uncertainty in data, planning is mostly everything. Feedback policy is crucial. I'm still impressed by all these BLA reflex reaction recovery, like about a second, because it only spit out 1 second. And then there's a lot of things that are amazing. But you also see a lot of like stupid reaction, like you can't even know it's grabbing, not grabbing. It's not grabbing. Like there's no idea how to crack. If you happen to be in the data set, it works. If it not happen to be in the data set, I don't know, right? Are we going to chase all this down and then collect that data more like the Tesla does? And then all these possible cases, just think about that. What is the right way to think about it? So, and eventually, we really want to tackle this, elderly situation to really help our humanity And this is significantly severe in Japan, and in my home country, the Korea is probably the worst. Korean and Japanese are very healthy. They eat really healthy. The problem is they're living very, very long. And the population discrepancy between old people to the young people are just like not measurable. Everybody hear about birth rate 0.7, 0.5, and so on and so on. So I really hope we can solve this problem all together, thinking about this way. Thank you very much.
Thank you so much, Professor Kim. Now we have 3 minutes to take a few questions. I'll go to the back first because you went last.
Hi, Dr. Kim. Thanks for sharing your insights. I just have one question about the reflex that you mentioned. So I just want to better understand like whether the innovation and challenge was in more hardware side on like coming up with more advanced like actuator, or was it more innovation on like a software algorithm, like designing how we like move each joint? So basically, was it more innovation on hardware or software? And related to that, I wanted to ask one other following question, where like in order to for us to move forward and achieve like more context-aware dynamic like physical intelligence, do you think the bottleneck is in like hardware side or in software side?
So in terms of like need for innovation, need for like new things, still like number one is architecture. I think all these there's once in a while there's some algorithm piece come out. Even transformer, take a look at it. Is that an algorithm success? It's an architectural success. Right? We're still doing backpropagation. So I think the number one is always architecture. And the same for those fungal gems like parkour, all that is architectural. Number two is algorithm. There's some algorithm may help them. And number three is probably the hardware. But the hardware is kind of funky thing because I think I mentioned that in multiple talks, like when you build a house, hardware is like your frame. Do you know how to build a frame? Do you know how to bolt those steel frame and then find the right wood to put together? Technology is there. We know how to do it. But if you put the wrong frame and then put the drywall, the paint, and then put the furniture and so on, and then at the end, like something's not right. And then if the software is wrong, you can repaint the wall, you can change your furniture, you can change your drywall. But if the hardware is wrong, you have to start from scratch. Because all the data collection, all the knowledge you accumulate is based on what that hardware can do. All the algorithm is going to rely on it. So that's where the difference between VLA and the rest of the game. VLA, they're all trajectory. So that's a common language. That's why I talk about common language in autonomous driving. If common language is trajectory, yeah, it doesn't matter which robot you're using. I guess the finger, if you have multi-finger now, is a little complex. But once the language is beyond trajectory, now it's going to be relying on hardware. If you start with the wrong hardware, well, I'm not saying wrong hardware, not the best hardware. All the work based on the hardware is going to be relying on it. And then if that's not the right hardware, you might have to start from scratch. So it's not about need for innovation, but it actually influences pretty huge. Yeah.
Makes sense. Thank you.
Yeah.
One more question.
Thank you for the very inspiring talk. My question is also on the reflective policy you talked about. I wonder what sensor reading do you need? Do you need a very good touching sensor for that? Or like you talk about visual is very important, but for that, I feel like maybe that's not the visual part from the sensor.
It's not visual. So everything we show is none of them are visual. It's all force-based, and then there's some vision-based. Those are proximity sensor, which is not camera. You can, so I can give you an answer. I don't even know what is the right set of sensor, and you have to think about the complexity and robustness and everything, right? So that's why I think we have such amazing vision policies, vision work. Vision is still progressing so fast, and I heard this like people. They have to read like at least 30 pages papers every day to catch up or something. So vision space is moving very fast, and then that's why all these companies are trying to take advantage of it. So they put the camera now on the hand, so they can actually get all these details. So maybe if you have a very flexible hand, and then this camera capture all that, maybe the contact force can be improved on. I don't know. So that's one way of thinking. A lot of companies are using those spin gripper that actually flex. And then if camera is right there, you can actually implicitly learn about the contact forces and everything. But I'm still a strong believer on like local policies. Either to talk camera based, either like actual contact force based. We need to have some local policy doesn't rely on this large model curing and takes long and so on. In order to really achieve a highly dynamic and then reliable action.
Thanks again. Let's thank Sangbae again, and he will be at the panel.